Hello, everyone. Uh, my name is Mehul Motani. I'd like to welcome you all to the inaugural talk of the seminar series, Information Theory in Singapore, ITIS. And also, welcome to Singapore. Virtual Singapore. Many of you are here in Singapore, but some are not. So, welcome to virtual Singapore. I wish I could welcome you to Singapore in person, but these are strange times. So, this will have to do. Behind me is the view from my office. So nice, right? Well, I wish it was a view from my office. Uh, this is the Singapore skyline. I hope this pandemic passes soon and you all can visit Singapore and see the beautiful country for yourself. So this is because when I looked at the registration list, there were a bunch of people from outside of Singapore. So I'm really excited about that. So the Information Theory in Singapore seminar is organized by a team that includes Han Mao from NTU, Tai Kui and Tang from SUTD, and me from NUS. And our aim is to promote, advocate, and spread the joy of information theory and coding theory within Singapore and now around the world. We have 5 talks lined up for this year, 2020, and we'll be putting out the 2021 schedule soon. So be on the lookout for that, and please spread the word. Okay, get people to register so we can remind them of when the talks are happening. So today is the first talk in our seminar series. Before we get going, let me address a few logistical matters. Please keep your microphone and video muted for the duration of the talk. If you have questions, just type them into the group chat and we'll address them in the Q&A at the end of the talk. All right, now it is my great pleasure to introduce Professor Vincent Poor as our speaker. Professor Vincent Poor is the Michael Henry Strater University Professor of Electrical Engineering at Princeton University, where he was the Dean of Engineering for many, many years. His research interests include information theory, machine learning and network science, and their applications in wireless networks, energy systems, and related fields. He has received many awards and honors. The list is too long to go through, so let me highlight a few. He's a member of the US National Academy of Engineering and the US National Academy of Sciences. He's also a foreign member of the Chinese Academy of Sciences and the Royal Society. He's an IEEE Fellow. He has served as Editor-in-Chief of the IEEE Transactions on Information Theory and as President of the Information Theory Society. Recognition of his work includes a 2017 IEEE Alexander Graham Medal and honorary doctorates from universities in Asia, Europe, and North America. I'm honored to have my colleague and friend Vince Poor share his thoughts with us today on physical layer security in wireless networks. Let us warmly welcome Professor Poor. Yay.
Thank you.
Okay, let me
Thank
hand
you
it
very
off to
much,
Vince.
Mehul, for that kind introduction. Welcome to my kitchen. This is my kitchen. This is where I live these days. I'm honored to be the first speaker in this series. I was in Singapore, I guess it was about a year ago. Is that right, Mehul?
Yeah, that's right.
And I had a really wonderful time there, and I wish I could be there physically. But maybe that'll happen next year. Anyway, I'm really happy to be here speaking to you tonight, this morning for you. And as Mehul said, I'm going to talk about physical layer security. I wanted to talk about something with an information theoretic content, given the purpose of this series. So let me see if I can share my screen here. I hope you can see that. Can you see that, Mehul?
Yeah, that's right. Yes, we can see it.
Okay, great. So I'm going to talk about physical layer security in wireless networks. And again, I'm subtitling it an information theoretic perspective, because there are a lot of aspects of physical layer security that don't really have much to do with information theory. And I want to thank a few people, Arsenia or Ursi Chordi in France, and her student Madi Herfe, and a former student of hers in Essex, Amiro Mitev, who helped with some of the slides I'm going to show you. Madi and Ursi and I have a chapter that's about to appear in a book on physical layer security, which covers a lot of things about physical layer security, not only the information theoretic aspects I'm going to talk about today. So I'll just call that out because people who may be interested in some of the other issues can look in this chapter when it appears, which should be pretty soon. So anyway, here's sort of a view, maybe oversimplified view of security today in wireless networks. Of course, networks are organized in layers, and today security is primarily applied. Security measures are primarily applied at the higher layers, mainly at application or transport layer. And it works pretty well for a cell phone. I think your cell phone's pretty secure. And so you might ask the question, why do we even need physical layer security when we already have a lot of really good solutions for security at the higher layers? There are some very good things about standard security, and I'm going to just talk about crypto systems now, although there are a lot of other aspects of security. For one thing, there are no known feasible attacks. I mean, the bits of random bits are large enough, number of random bits are large enough that the the computational complexity of trying to solve for the key in the known crypto systems is infeasible with today's technology. And it's been widely employed and tested, and authentication is trustworthy. So we kind of trust our security today. We do banking and so forth without really worrying too much about it. On the other hand, just from a broader perspective, it's built on unproven assumptions, namely the difficulty or the perceived difficulty of certain mathematical problems. Also, it assumes that the physical layer is already there. You have a connection at the physical layer that you can use for over which you can implement cryptography. It's computationally intensive. So for some applications where the terminals are of low complexity, that might be a problem. And it requires infrastructure, which may not be, in some emerging types of networks, may not be something we can take for granted. Now, physical layer security has some advantages. First of all, it's quantum secure. It's based on fundamental physical layer principles, at least what I'm going to talk about today is. The key can be generated on the fly from common randomness in the channel. You don't need key distribution. And it's really lightweight. That is, you really only need the kind of complexity you need for error control coding to do certain kinds of physical layer security, at least in terms of data confidentiality. Now, there's some negative things. One is a lot of what's known about physical layer security based on information theoretic security makes some assumptions about the eavesdropper's channel, which may or may not be practical. Also, there's a lot of it is asymptotic theory. So finite blocks are not as, finite block length theory is not as well developed, although I'm going to talk a little bit about some of that here. And it's still in its infancy. We haven't really seen a lot of implementations of physical layer security in practical systems. But a prime example of what's wrong with some of the shortcomings of more traditional security methods is the Internet of Things, where potentially tens of billions of devices, in other words, massively deployed networks are going to be out there communicating, and sometimes without much infrastructure, sort of a grant-free type of access, with sometimes fairly low complexity terminals like sensors and so forth. So here's an example where the current type of higher layer provision of security could break down. So this is a place where where physical layer security might provide solutions that we just can't provide in other ways. And so, and for IoT, security is a major concern. There's been a lot of publicity about IoT security. You can read it in the press all the time about, hacking of various kinds of IoT devices. And since these devices are going to be used for security, for physical security, and for things like healthcare and so forth, there's a serious concern that the security of IoT will not stand up to the societal importance of some of these applications. I mean, one example, let's see here. One example of what can go wrong is in this paper from Usenix a couple years ago, where we looked at what would happen if a botnet could get loose and control a lot of high wattage IoT devices. So if you have a Nest in your house controlling your air conditioner, refrigerator, and so forth, what might happen if you get a botnet the size, say, of the Mirai botnet, which was a botnet that brought down the internet, and got control of something like water heaters, okay? And it turns out that with something like this, a Mirai-sized botnet controlling water heaters, you can change the demand for electricity instantly by 3 gigawatts, okay, which is on the same scale as the largest currently deployed nuclear plant. So using, just using the vulnerability of IoT, it would be possible, at least in principle, to inflict damage on the electricity grid equivalent to flipping off and on the largest nuclear plant out there. Okay, so you could cause cascading failure or other tripping of generators and so forth, all the kinds of things that kind of change in load would instigate. So there's a lot that can go wrong, and so this is a serious issue. So what can physical layer security offer? Well, there's multiple levels of security, of course: node authentication, message integrity, message confidentiality, and so forth. And there are different aspects of physical layer security that address these various functions. Now today, some of them are not information theoretic, okay? There are information theoretic issues in all of them, but most of them are, many of them are not information theoretic. But one place where information theory has a lot to say is in the issue of message confidentiality. And so that's what I'm going to focus on in my talk today. So here's an overview of what I'm going to talk about. First of all, the theme is a role for information theory in this area. This is an information theory seminar. I'm going to focus on two things: message confidentiality and data transmission, and privacy and sensing systems. So this is focused on IoT type applications. And then at the end, depending on how much time I have, I might talk about a few other issues where information theory has something to add: authentication, security in mobile ad hoc networks, and attacks on sensor networks. We'll see how much time I have. So let's talk about message confidentiality. So first of all, let me repeat in a little bit different words what I said at the beginning. Security in wireless networks has traditionally been a higher layer issue. And that's particularly true also of message confidentiality, where the main technique is encryption. Okay, so there you deal with all the issue of key management and so forth. Now, as I said, if you have a massive number of devices, especially with no or light infrastructure, this is going to be a problem. And also if you have low-cost terminals, and increasingly of importance is low latency. And if you do encryption, you add to the latency, right? So, low cost, low latency networks, URLLC type things, with massive numbers of them is going to be a problem for conventional approaches to message confidentiality. So again, physical layer security provides security by exploiting other things than the difficulty of computations and so forth. Namely, it exploits imperfections in the physical channel. And in the wireless channel, we're talking about noise, fading, and so forth. And the idea of physical layer security, at least for message confidentiality, is to replace something you're already doing, that is error control coding for reliability, with joint coding for reliability and security. So the complexity of this kind of thing is more or less like the complexity of error control coding rather than the complexity of encryption. So let me say a little bit about, I'm going to kill that if I can. Let me say a little bit about the genesis of using information theory to try to understand security. And that goes back, like almost everything else in information theory, to Shannon. Shannon, in his 1949 paper, so not his most famous paper, but his 1949 paper, he looked at the issue of secrecy in cipher systems. So he looked at a three-terminal network where you have Alice, a source that wants to transmit a message to a legitimate receiver, Bob, in the presence of an eavesdropper, Eve, who can, just like Bob, can perfectly see the output of Alice's transmitter. Okay, so there's no noise in this model. But Alice and Bob share a secret key. Okay, so Alice is going to use the secret key to encrypt her message or to encipher her message, and Bob knows that key, so Bob can decipher the message. Eve does not know the key. So Shannon was interested in what are the conditions on the key that need to hold so that these messages can be sent in perfect secrecy. And Shannon, in this context, had good news and bad news. The good news was, with such a model, you can transmit a message in perfect secrecy. But the bad news is that in order to do that, the entropy of the key has to have as much entropy as the source that you're trying, or the message that you're trying to transmit. Now, so that's kind of bad news, because, at least for us, because if we're in a wireless network, that means in order to get perfect secrecy in an encipherment system, we need to have another channel or some way that we can transmit as much key as we have message. Okay, so that means that I'm trying to get rid of this. Maybe if somebody could admit this person, that would get rid of that. Here we go. There we go. So that's bad news, because for a wireless network, that's just not going to work. And in fact, Shannon was interested in a one-time pad system like this, but it was a radio telephone system during World War II, between Roosevelt in the United States and Churchill in London. And they did have a one-time pad system. So they were able to put the key on a recording, which could be carried physically to London, so that they had a back channel where they could carry the key. But in a wireless network, we just can't do this. And in fact, very few, if any, modern crypto systems use one-time pads. Most of them use a key with a much lower entropy than the message that it's going to encrypt. And then that key is blown up into a longer key using something like public key, where the security of that is not because of its entropy, it's because the difficulty of computing, reversing the computations that are used to create the key. Now, so this is Shannon's take on this problem. Now, if we zoom forward into the 70s, another way of looking at information theoretic security is due to Aaron Weiner. So Weiner had the same three-terminal model, Alice, Bob, and Eve, but he recognized that in real channels, communication channels, there's noise. So there's a noisy channel between Alice and Bob, and another noisy channel between Alice and Eve, not the same one. So Weiner took away the secret key. So now Alice and Bob don't share any secret at all. They just have a different noisy channel from Eve. And Weiner was interested in the question as to whether you could transmit reliably to Bob while keeping his message in complete secrecy from Eve. So he looked at the trade-off between the reliable rate to Bob versus the equivocation to Eve. So the equivocation is just the conditional entropy of the message given Eve's measurements. Okay, so if that equivocation equals the entropy of the message, then Eve doesn't get anything. Or if another way to look at it is if that entropy, that equivocation equals the rate to Bob, maybe the rate is less than the full message rate, whatever's being transmitted is kept in secrecy to Eve. So Winer defined the secrecy capacity of this so-called wiretap channel to be the maximum reliable rate to Bob, such that the reliable rate equals the equivocation at Eve. And Winer had good news and bad news too. I mean, his good news was that the secrecy capacity can be positive in such a setting, but that it's positive if and only if Z, that is Eve's measurement, is somehow degraded relative to Y, Bob's measurement. Okay, so for example, you might think about Eve having a lower signal-to-noise ratio in a Gaussian channel. Okay, so now Winer wasn't thinking about wireless because, well, first of all, the name of his channel is the Wiretap channel. He worked at Bell Labs. It was a telephone company, and this was in the 70s before the widespread use of wireless in modern communications like we have today. But that use of wireless has created a resurgence of interest in these ideas in our day, okay? Particularly because of some of the reasons I mentioned, connecting to IoT and other networks of that type. So in general, the message we get from Shannon and Winer is that somehow in order to transmit in secret, the legitimate receiver has to have some kind of advantage over the eavesdropper. It has to be either a shared secret with the transmitter, like in Shannon's model, or a better channel, like in Winer's model. Okay, so now that's sort of the insight we get from those two studies. And now, how does that play out in wireless channels? Okay, well, wireless channels have some good physical properties, namely diffusion and superposition, that provide opportunities for this. So diffusion and superposition cause fading, which, as we know, is good for us in terms of reliability and diversity. But it also provides natural degradedness over time. So the eavesdropper can be degraded by fading. And if we can take advantage of that, then we're getting some free secret transmissions without using a secret key. Also, interference, which is part of the superposition property of radio propagation, allows active countermeasures to eavesdropping. That is, we can jam an eavesdropper, and that degrades it, right? And also, we can use spatial diversity, that is, multiple antenna systems, relays, and so forth, to help us create secrecy degrees of freedom. So all these radio properties that we take advantage of for other reasons are also useful for degrading an eavesdropper. Another property of radio channels is that they're random. That comes from, of course, diffusion and superposition and the sort of random nature of reverberation and so forth. And that gives, but they're also reciprocal. So that means two terminals who are communicating one another see the same channel gains in each direction. So that's a source of common randomness that two terminals, a receiver like Bob and Alice, can use for key generation. Okay. Of course, an eavesdropper has a different channel, so the eavesdropper can't really tap into that common randomness. So the first of these three phenomena have been extensively explored to develop secrecy capacity regions for all the fundamental channel models that we usually use to understand wireless networks. I'll say a little bit about the fourth one in a minute, but let me talk about that now. So here's the main models. We have a broadcast channel, a single transmitter, multiple receivers, multiple access channel, multiple transmitters, a single receiver, interference channels, multiple transmitters, multiple receivers, relay channels, MIMO channels, and so forth. And all these channels have been examined in this through this lens of information theoretic security. There's some distinctions. For example, the multiple access channel, we don't usually worry about cross communication between the transmitters, but in this case, those are the eavesdroppers. If you have two transmitting terminals transmitting to a common receiver, so this is a uplink problem. You might think of the other transmitters in the multiple access channel as being eavesdroppers on their counterparts. So you have to think about a slightly more complicated multiple access channel, but that can be used to examine the information theoretic security of this channel. So I'm not going to talk about all of these. I'll talk about the first one briefly, but there's a paper with Raphael Schaefer in the Proceedings of the National Academy of Sciences that covers a lot of what was known, at least up until 2017, in these areas. So let's look as an example, though, at the Gaussian broadcast channel. Okay, so here, and this is actually the so-called broadcast channel with confidential messages. So here we have one transmitter and two receivers. There are two messages. One is a message that's a broadcast message for both receivers, and one is a confidential message. So M2 is a confidential message that should be transmitted to Bob 1, that is the top receiver, and kept in secret for the bottom transmitter, the bottom receiver, I'm sorry. So with regard to message M1, the lower transmitter is a legitimate receiver, but with regard to message M2, it's an eavesdropper. So for M1, this is a broadcast channel. For M2, this is a wiretap channel. So you might think about this as a model for a content distribution system where some content, like the common message, is basic content that everyone in the system receives. And some content, like M2, is premium content, which is intended only for those who paid for it. Okay, so that's the way to think about it. And so not naturally in this system, you don't want those who haven't paid for it to be able to read that message. So what I've shown here is for the case where the signal noise ratio at the top receiver is 10 dB and the signal noise ratio at the bottom receiver is 5 dB, I've shown the capacity region. So the red, so along the horizontal axis is the common message rate, and on the vertical axis is the confidential message rate. And if we don't impose confidentiality on that message, all the rate pairs below the red line are feasible or achievable, and that's the capacity region of that broadcast channel. On the other hand, if we impose perfect secrecy on the message M2, the blue dashed line shows the outer bound of the secrecy capacity region. So you can see what happens is the rate for the secret message in this case drops, and that additional capacity between the dashed line and the red line is capacity that it's used to confuse the eavesdropper. So there additional code words are used that don't really carry information, but rather are used to confuse the eavesdropper. And if we look at what happens versus the signal to noise ratio of the secondary receiver, it looks something like this. So here we fix the primary receiver, the top receiver, to have 10 dB of SNR. And the other receiver, we look at what happens as we vary the SNR. And in particular, as we decrease the SNR, you can see that what happens is the range of common rates shrinks and the range of secret rates increases. That's just because in transmitting the common message, the secondary receiver is the bottleneck. So if we lower its SNR, then we're naturally going to lower the rates at which we can transmit that message. On the other hand, as we lower the SNR at the secondary receiver, it's easier to transmit the secret message. So you can see that happening here. Now, note that the signal noise ratio at the secondary receiver is always less in this case than that of the primary receiver, so we're always in a degraded situation. Now, Winer tells us that if the secondary receiver has signal noise ratio of 10 dB, then the secrecy capacity region would collapse. Okay. Now we get a little bit different story if we go to the fading Gaussian broadcast channel. So this is the same channel, except now we assume the noise level at both receivers is the same, but there's fading between Alice and the two receivers. And the fading is Rayleigh, and it's Rayleigh with unit parameter going to Bob 1, I should say, and it's Rayleigh with parameter sigma 2 going to the other receiver. Now, if you remember your communication, you know that a smaller sigma 2 means more intense fading. Okay, so that's like more degrading more the secondary receiver. And here we see the same kind of thing. As sigma 2 gets smaller, the rate of common rates, the range of common rates diminishes, and the range of secret rates goes up. But a distinction here between the Gaussian broadcast channel is that we never lose, the secrecy capacity region never collapses here. So you can see that the red line is the case where the two channels are statistically identical. And so there's no degradation or anything here. But in fact, the secret message can still be transmitted with positive rate. In fact, pretty healthy rate, okay? And what's happening there is basically that, you know, even though statistically the two channels are identical, there are times when the secondary receiver is going to be degraded just because of the fading fluctuations and so forth. So during those times, secret messages can be transmitted. And when the first receiver is degraded, you can use that time to transmit the common message. So that's how you can take advantage of fading here to get a positive secrecy rate, even when you have a non-degraded eavesdropper. So now I want to talk a little bit more about the Wiretap channel, though. That was the broadcast channel, and talk about another issue. So just going back to Winer's channel, this is just a different picture of it. So here's the basic setup. We have a message, now I'm calling it W. It's going to be encoded into N channel uses. It's going to go in the channel. And then there are two outputs of the channel. There's Bob's output and Eve's output. So you get N output symbols for each. And then Bob is going to both are going to try to recreate the source. And we're interested in having Bob recreate it perfectly, and Eve not be able to recreate it at all. So we can look at the leakage. We can look at the epsilon, the error at Bob's output, which we want to go to 0, and the leakage at Eve's output, which we also want to go to 0. So leakage would be a measure of equivocation or something like that. So the way we get Winer's result is we let the block length go to infinity. So this is a classical asymptotic information theoretic formulation. Let the probability of error go to 0, the information leakage go to 0, and then we get the secrecy capacity. And under some conditions, not all conditions, but under some conditions, that capacity has a very nice formula. It's just the maximum over the input distribution of the mutual information, of the difference in mutual information between Alice's channel to Bob and Alice's channel to Eve. Okay, so this is not a completely general formula, but it's somewhat general. So that's basically Winer's result, maybe oversimplifying a little bit. But the limitation of this result is that it's asymptotic, right? So the block length goes to infinity, which is a problem. Okay, so how can we deal with that? Well, let me just remind you of something else in information theory, and that is finite block length information theory. So the most classical problem in information theory, the most basic one, is the top picture at the top here. So we have a source W that has M possible values. It's encoded by an encoder into N channel uses. Those channel uses go into the channel, or those channel symbols go into the channel. They create output symbols. Those output symbols go in the decoder, and the decoder tries to reconstruct the source with as much fidelity as possible. So in such a model, we're interested in an NM epsilon code, where for a source with m possible values, so log 2m of bits, which we'd like to be reconstructed with fidelity no worse than epsilon, using n channel uses, okay, we're interested in a fundamental quantity, which is the maximum m star that we can get with that we're given n and epsilon. So that's the capacity of the channel, if you will. Okay. So now we know that if we take the log of m star and divide by n and let n go to infinity and epsilon go to 0, we're going to get the channel capacity. That's Shannon's basic result, or one of Shannon's basic results. But what if we're in a situation like IoT or some other kind of latency constrained application where we can't let n go to infinity, and we're not going to get epsilon going to 0 either in that case? What can we do? Well, in Yuri Polyansky's thesis 10 years ago, he developed a formula for that. So basically, the log of m star has a leading term n times the capacity, which you know it does from Shannon, but it also has a correction term. The second order term is a root n term, which is multiplied by the inverse of the Gaussian tail, the unit Gaussian tail evaluated at epsilon, times another quantity called the dispersion, v. Okay, so what is the dispersion? Well, the capacity, as you know, is the expected value of the information density evaluated at a random variable that has the distribution of the optimal input distribution, and the output, a corresponding output, a random variable has a corresponding output distribution, x star and y star. So the first moment of that random variable is the capacity, and the variance of that random variable is the dispersion. That is the next term in the expansion of the capacity, if you will, which is a 1 over root n term, if you divide everything through by n, is the variance of the same random variable that the leading term is the expectation of. Okay, so this is a very good formula. We can look at it for a particular case. This is an additive white Gaussian noise channel with SNR of 0 dB and epsilon. This is the bound on the error probability of 10 to the minus third. This particular channel is chosen so that the capacity is 1/2. And then what we show here is versus n, the log of m star over n. Okay, so it's the rate, the maximum rate. And we don't have the exact expression for it, but we have an upper bound for it, converse, and we have a lower bound for it, which is an achievability result. And it has to be squeezed between those two. And the approximation that you're seeing there is a modification of that formula I just showed you. Okay. And so you can see that, first of all, that we have a really good handle on what the actual capacity is. There's not much room between the converse and the achievability bound. But also you see that for small packet sizes like you have in IoT down in here, there's quite a bit of gap to capacity when you go to finite block length. Okay, so that's kind of a message for general communications. And what does that say about the Wiretap channel? Well, more recently, with Wei Yang and Raphael Schaefer, we looked at the Wiretap channel in the same context. So here's Weiner's Wiretap channel, the same model I showed before, except now we're not going to let n go to infinity, and we're not going to let epsilon go to 0, and we're not going to let delta go to 0. So now we have a maximum secrecy rate, which is depending on n, epsilon, and delta. So just like in the case of the normal transmission, we have a maximum rate depending on n and epsilon. And then we can look at different types of channels. We don't have a general formula for this, but we can look at different types of channels. So this is the the so-called semi-deterministic wiretap channel, where with a binary symmetric eavesdropper channel. So here the legitimate channel is deterministic. The eavesdropper channel is a binary symmetric channel. And the rate is a function of block length, fidelity, and leakage has a very similar form to the Polyansky formula. There's a slight difference here. V is a different, this is not the usual dispersion, it's a dispersion related to the secrecy capacity. And delta, we also have delta and epsilon here that we wouldn't have ordinarily, okay, in the other case. But here for this channel, you can see a very similar picture. This is the secrecy capacity here. The asymptotic secrecy capacity of Wiener is 1/2. But again, so we have an achievability bound and a converse. And again, you can see that for small packet lengths, there's quite a gap between the actual secrecy rate, maximal secrecy rate, and the secrecy capacity. Okay. Now, we can also look at, this was, by the way, at IT Symposium in 2017. But you can also look at the Gaussian wiretap channel. Here's a similar one. This has, this is a typo here. This is, Bob's SNR is 3 dB. Eve's SNR is -3 dB. So this is a degraded channel. Epsilon and delta are 10 to the -3. I didn't write that on here. And now we can see a similar result, although the gap between the achievability and the converse bounds is much bigger. But somewhere in here is the actual maximum secrecy rate. So again, no matter where you are in there, there's a pretty big gap to the secrecy capacity. All right, well, I'm going to, let me mention just very briefly, I'm not going to talk much about key generation, but key generation, as I said, can be derived from channel reciprocity. That is, Alice and Bob can both estimate the channel gain, for example, and that's a shared secret. There are other ways to do that. You can use public discussion. This goes back to Yuri Maurer back in the 90s. Also, you can look at relays to help you distill key and so forth. I'm not going to talk about that here. I'll just point out a book chapter, and I'm going to come back to references later, but I'll just point out a book chapter that talks about these various issues. And that chapter I mentioned with Ursi and Mahdi also has some of this material in it. Okay, so I've got 15 minutes, so I want to shift gears and use maybe 10 of those to talk about privacy. First of all, so far I've been talking about secrecy, that is transmitting a message from one transmitter to a legitimate receiver and keeping it secret from an eavesdropper. Okay, so that's privacy, that's secrecy, but that's different from privacy. In privacy, you don't really have an eavesdropper, or there may be one there, but that's taken care of by security issues. In privacy, you're worried about the actual legitimate receiver getting information beyond the information that you'd like him to receive. Okay, so the eavesdropper here is not a malicious actor necessarily. It's somebody that you trust and you want to share information with, but you don't want to share everything. Now, you don't want to apply secrecy here because denial of access, that is secrecy, would make the data source useless, right? So we have to think about this another way than if we were just trying to provide secrecy. And we can do that through the so-called privacy utility trade-off. So we can think about IoT systems are generating a lot of data. Okay, so they're data sources, and that data is being generated because it's useful, right? So the utility of that data depends on its accessibility. So at one extreme, you'd like to make the data as accessible as possible to get the maximum amount of utility. On the other hand, accessibility to the data endangers its privacy. So at the other extreme, you might want to keep the data completely secret in order to preserve privacy, maximally preserve privacy. So there's a fundamental trade-off between these two opposing goals. of making the data accessible and giving it utility, and making it inaccessible and making it private. So that's a fundamental trade-off that we can characterize using information theory. And so an example would be to, for example, to measure utility in terms of distortion, sort of as an inverse measure of utility, and to measure privacy in terms of equivocation. So the more distorted the data is, the less useful it is, or the less distorted it is, the more useful it is. And the greater the equivocation at Bob, the more private the data is. Okay, and we can actually analyze that. It's like a rate distortion problem with an equivocation constraint. So we can actually, for various models, we can derive this, the region of potential equivocation utility points. And that gives us a utility privacy trade-off region. And it has an outer boundary, which is an efficient frontier, if you will, that tells us what the trade-off is optimally. So it doesn't tell us where to operate. It just says, well, if we want to have a certain amount of privacy, then that's how much utility we can expect. Or if we need a certain amount of utility, we're going to have to give up a certain amount of privacy. There's no way around it. Okay, so that's an information theoretic problem that comes out of this idea of privacy. So I'll just, as an example, I'll talk about smart metering. So smart metering, electric meters are used for price-aware usage, load balancing, and so forth. It's useful. There are smart meters everywhere now these days, and they're useful. That's why they're there. But you know, it's well known that smart metering leaks information about in-home activity. You can tell what's going on in the house to a certain extent by looking at the smart meter trace. So there's a utility privacy trade-off in smart metering, and it can be studied in this context. In particular, if we model the, so one of the things, a lot of the privacy is given up by these transients. So if you turn on the toaster, you turn on the oven, the TV or something, the coffee pot, that's a definite activity that somebody knows someone's in the house or knows where you are in the house and so forth. So those intermittencies are somehow the most privacy revealing. So we can think about modeling the trace as a hidden Markov model, and we're trying to protect the hidden intermittency state. That's what we're trying to protect from being released. And it turns out that we can, if we formulate this problem this way, we can see that the privacy utility trade-off leads to a spectral reverse water filling solution. That is, a spectral reverse water filling solution. That is, we look at the spectrum of the trace and we draw a water level phi, and all the components that are below, whose energy or power is below phi, we suppress, and those whose power is above phi, we allow through. And the idea here is that we're suppressing those transients which have low average power, and we're allowing things like the air conditioner and the refrigerator and so forth, where most of the power is being consumed, to go through in terms of the usage, measuring the usage. And then if you move the water level up and down, you basically trace out the efficient frontier. That is, lower water level is greater utility and lower privacy. Higher water level is less utility and more privacy. Another way to approach this problem is through using control. We can have, if we have a battery, then we can control the battery storage in order to minimize information flow out the meter to the utility provider. And then we have a trade-off between information leakage and wasted energy, because by doing this, we may waste some energy. We're not optimizing energy usage, we're optimizing privacy. And this is a problem that turns out to be a Markov decision process. It's very complicated to solve analytically, but we can solve it numerically, and for certain under certain simplifying assumptions, we can trace out the trade-off region. All these dots are various points in the region, and we can get the lower boundary of that, which is the efficient frontier, which tell us the optimal trade-off in this case. Now, another problem in this general area is that of competitive privacy, where we have, and this is maybe applies to certain sensing applications and things of that sort, where we have multiple interacting but competing agents that have coupled messages. So, sorry, coupled measurements. And in each of these agents wants to estimate some parameters that it has, its own state. But since they have coupled measurements, they can help each other by sharing data. But on the other hand, if they share data, they risk compromising privacy. So each one of these agents has a privacy utility trade-off, but it's in a competitive environment. So for situations like that, we might ask, well, how should such agents interact? And just to give you a couple of examples, I got interested in this problem through the electricity grid, where you have multiple companies sharing the same distribution grid or transmission grid, depending on which level you look at. And so they have to manage that grid. They want it to be optimized. Load matches demand, but they're private companies. So by sharing, so if they share data, they can optimize state estimation of the grid, but then they are at risk of maybe giving up some private information. So, you know, they have this is a competitive privacy situation. Another situation might be in a battle where you have allies who are really just allies because they have a common enemy and they don't trust each other, but they want to defeat that enemy. So they want to share information, but they're worried they don't want to share too much because they want to help each other, but they don't want to, they're not completely trusting each other. So they don't want to share everything that they have. So that's another area of another problem that might come up like this. And finally, in a sensor network, you might have, say, doing underwater oil exploration, you might have two different companies in the same general area looking for oil, and each of them could benefit from knowing the other's data, the other's measurements. But on the other hand, they don't necessarily want to share because they're competitors. So again, this is an issue of competitive privacy where you have each agent has a benefit from sharing, but also it has a risk of giving up some private information by sharing. So we can look at this problem information theoretically. We can set up linear measurement model where each agent measures a linear combination of all the other agents' state in noise. So the utility for a given agent is the mean squared error for its own state. So it wants that to be as small as possible. The privacy is, again, an information leakage to other agents, mutual information type leakage or equivocation. And if we set it up this way, we get basically another classical information theoretic problem. It's just the Wiener-Zipf problem. That is the optimum distributed source coding problem. So that tells us immediately how these agents should exchange information. But what it doesn't say is how much information they should exchange. That is, it just says what to do when you decide to exchange information. It doesn't say where to operate on the trade-off between privacy and utility. So here, because it's a competitive problem, it's a game theoretic problem, and this leads to a lot of interesting problems as well. I'm not going to get into it, but you can see the value of pricing, multiplayer games, cooperation, and so forth in terms of giving this problem meaningful solutions. All right, I'm about out of time, so I'm just going to mention these other issues quite briefly. So other primitives that we're interested in, among other primitives we're interested in, one is authentication. And it's also something that can be looked at information theoretically. And I'll just mention that there are ways of developing information theoretic bounds on impersonation and substitution attacks using information theoretic ideas. Also, attacks on mobile ad hoc networks where you have mobile nodes and all the messages are being transmitted by peer-to-peer forwarding. Well, if some of the nodes are malicious, how does that affect the overall secrecy capacity of a network like this? Okay, And the scaling laws for that can be derived in this paper that I mentioned here that does that. And then finally, we can look at attacks on sensor networks, man-in-the-middle and spoofing attacks, also from somewhat of an information theoretic lens, where we analyze the Cramér-Rao lower bound. It's not exactly an information theoretic quantity, but it's related, based in the presence of these kinds of attacks. So I'm not going to talk more about that because I'm about out of time, and I'm just going to flip through that, and then I'll just wrap up with a couple of comments, and then I'll take questions. So the basic message here today is that information theory can help us understand some fundamental limits of security and privacy in wireless networks. Of course, everything I've talked about here is theory. It's information theory, it's theoretical constructs, just like other aspects of information theory. Although sometimes they point to potential practical solutions, like in the smart meter example. In order to use this in real networks, we need a lot of things, like more finite blocklength analysis, scaling laws for large networks. All I talked about were just small two-terminal networks, 2-3 terminal networks. Practical coding schemes, there's been a lot of work in this area, so there are some things, but again, a lot more needs to be done. And then, as I mentioned at the beginning, other security primitives, signatures, certificates, and so forth. And then one point I'd like to make here is that one of the issues that often comes up with physical layer security is that it's not really ironclad. That is, it's based on certain assumptions about eavesdropper, or maybe certain conditions for the eavesdropper, which may not hold all the time. So, you know, if you're going to do banking or make war, you might want to use encryption. But if you're going to do, if you have like a sensing system or a content distribution system, you may not worry so much about having bulletproof security. So, for example, in a content distribution system, all you really care about is disrupting the content enough so that an eavesdropper, or a non-premium user, if you will, is not going to want to watch the content that's being disrupted all the time by channel conditions, okay, using a wiretap code. So we can think about a quantity like quality of security as a parameter. So if we want bulletproof security, that's one kind of security, and we need to go all out and use heaviest encryption we can. But if we don't want to pay for that, or if we can't do it, we might want to use best effort security. And then we can just set a level of security, quality of security, just like we do quality of service today in networks. So I think we should think about, when we think about physical layer security, we should be thinking in these terms rather than thinking about trying to replace necessarily the kinds of things that we use when we want to go do our banking and that sort of thing, which really can't be best effort. They have to be bulletproof. Okay, so let me just wrap up by showing these references I mentioned. There's a book at the top, Cambridge University Press, the paper in PNAS I mentioned early on, some other papers here that I mentioned through the course. I'll just mention one other thing that I didn't mention is the fifth one down here with Simi Yagli and Alex Ditso. When you talk about Internet of Things, one of the things you're thinking about is machine learning, because their data collection, largely data collection, is the main purpose of IoT devices and control. Federated learning, of course, is one of the main learning paradigms for that kind of setting. And information, and of course, privacy leakage is one of the concerns with federated learning, even though it's so supposedly privacy preserving, it's really not, because privacy can leak through the model or through the model updates when they're transmitted. So one thing you can use information theory here for is to develop bounds on those on that leakage. So there's a Spock paper that appeared earlier this year that develops that. I think with that, I'm done, and I'm happy to take questions if there are any, and if we have time. Thank you.
All right. Thank you very much, Vince. That was a great talk. At this point, we do have time for questions. So, are there any questions? If you have, just type them into the group chat. Okay. Please feel free to ask. Any question you want. Vince will give you some great answers.
Huh.
All right, Vince.
Any hard, I'm going to
What?
ask Mehul to answer any hard questions.
No problem. Okay, I'm gonna start off with the first question. Okay, Vince,
Okay.
can you elaborate a bit more on the difference between privacy and secrecy?
Yeah. So, well, yeah. So, I mean, of course, you can make things private from eavesdroppers by making it secret, right? So, in some ways, privacy and secrecy are the same. But there's also another aspect of privacy, and that is when you're sharing information with a trusted party, you may not want to share everything, right?
Okay.
So, for example, on Facebook or a social network, you're one of their customers. You're in their network. Presumably, you've allowed them to, see your transmission. You're not encrypting things to prevent Facebook from seeing what's on Facebook. But you don't want to share everything, right? So they're like someone like a trusted party, but not complete, right? So privacy is like you have some things you're willing to put out there and some things you want to keep to yourself. And so with security, you want to make everything opaque. Whereas privacy, you want to share some things, but maybe keep other things private. So it's that with privacy, it's more like the receiver is not really malevolent. It's just not someone that you want to share everything with.
Okay.
I don't know if that helps at all, but
Yeah, yeah.
that's
So yeah, I
way to
mean,
look at it.
so in some sense, you're saying secrecy includes privacy, right? But
Well, yeah, I mean, you might think of secrecy as being an extreme of
right.
privacy.
Okay. All right. Great. Okay. Thanks. Okay. Let me while waiting for people to type out their questions. Um, Vince, it really could be the case that your talk was so crystal clear, like maybe everybody is just enlightened. So let me ask one more question.
Sure.
When you talked about information theoretic results for physical layer security problems, like so essentially you're using like to prove these results, the techniques are asymptotic and not constructive. So what I want to know is like, can you maybe just share or maybe give some pointers? Are there practical coding schemes for these
Yes.
types of problems? Yeah.
Well, I mean, there are, yeah. So, yeah, just like other information
Right.
theoretic
Yeah.
proofs, the proofs use random codes, right?
Yeah.
So they're not practical. But you just like with ordinary, data transmission without secrecy, there are codes that approach capacity, right? There's
Yeah.
LDPC or I don't know, polar codes and so forth. Same thing here.
Yeah.
There are other codes. You can use LDPC codes, for example,
Hmm.
or you can use polar codes. People have used these kind of codes. Maybe they don't achieve capacity, but they can approach capacity. But the fundamental idea is that you use some code words
Okay.
to confuse the eavesdropper. So it's not too hard to conceive of codes, but you've got there are issues of how good are they and so forth and so on. But you might think about you have some code words that are just purely there to confuse the eavesdropper. And so you can do that with any code. You don't have to do it with a random code.
Yeah.
To prove things, you want to use a random code for obvious reasons. But for constructing a code, you want to use something you can decode and you can easily, with low complexity and so forth. So there are LDPC codes for wiretap codes and so forth. But there are limitations, and just like in any system, I think there needs to be a lot more work done in those on that problem before you'll have one in your
Okay.
nest. Yeah.
All right. All right. Cool. So let me just make sure everyone understands. If you have questions, just type it into the group chat. Otherwise, Vince and I are going to continue having a really nice chat. So while waiting for people, I have one more question. Can I keep going?
Yeah, absolutely.
So this is kind of a broad audience, right? And our goal is to sort of spread information theory ideas, coding theory ideas to a wide to sort of a wide audience. So let me share something that maybe first came to my mind when I started thinking about these problems. So typically, when you think about like about security, what comes to mind is cryptography,
Right.
right? Like it's not information theory, it's cryptography. Oh, I can just encrypt stuff. I don't know, just maybe for a wider audience, are you able to just share how is like cryptography related to some of the things that you spoke about, which is also has the word security, but it also talks about coding and information and stuff. Like how are these two related? Is that something that?
And so cryptography is applied on top of, typically in a communication system, cryptography is applied on top of the system. So you encrypt the message before you transmit it through the system. So someone can intercept the message, but they can't decrypt it. So that's how cryptography works, at least in terms of data transmission. And so you have to have a key or some kind of way of computing key. And the way that works, I mean, if you were to have enough key, it would be absolutely impossible to break encryption. And
Right, it's just a one-time
what
pad, right?
Shannon showed, right?
Yeah.
But that's too expensive. You can't really have as much key as you'd like. So the way encryption system works is they have a small key, 256 bits, not so small, but relative to the message that it's being encrypted, it's pretty small because you're sending out megabits or gigabits, right?
Yeah.
So the reason that's secure is because those 256 bits are used in a clever way so that in order to decode it, you have to be able to solve a certain mathematical problem that's very, very hard to solve. And so the computers today can't solve those problems, so they can't decrypt those messages. But in
Okay.
principle, it's not proven that those problems are hard. It's just thought that they're hard, and so far that's held up. But
Yeah.
in principle, if you had another kind of computer, like a quantum computer, you might be able to solve those problems, and then the security would just disappear. You wouldn't be secure anymore. So
Okay.
physical layer security takes advantage of the physics, not mathematics. It's more physics-based than mathematics-based. It takes advantage of the fact that the radio channel has certain undeniable physical properties that you can't undo.
Right. Right.
And
Exactly.
so that's really what this is about. But of course, and also we can use mathematics to prove certain things about it, but it all relies on models. So that's where the flaw in this is that it relies on models. So there needs to be more development of practical systems and so forth so that those models can be verified in practice. So I think that's what I would say the difference is. One relies on the difficulty of computational problems, and one relies on physical modeling,
Okay. But you're
which is
saying they
what,
typically apply together, right?
yeah, yeah, exactly.
All right, great. All right. So I was looking through the participant list, and I recognize some names, so um, I'm gonna error them to try to ask a question. All right. We have one of my PhD students, Chekting, is here. So Chekting, if you have a question, please type it out. And then there's some other really smart people, much smarter than me, who are here. So and they work in this area. So John, I can see you. If you're actually online, you wanna pipe in? You wanna ask a question? So while we're waiting for people to um, ask their questions, like I said, we don't need to have questions. We can, Vince, you and I can just continue having our chat. So one last question for you, which is, so you mentioned that you were interested in this because of sort of like sort of energy systems, right? Like that's how you got interested in the problem. Can I check in your experience and talking to the energy companies? Do you find that they're open to these ideas, or like have you seen any actually real world implementation or move towards that, like to try to build physical layer security in?
Well, First of all, I got interested in the privacy problem for energy systems,
okay.
not necessarily the security problem. I got the physical layer security. I got interested in because of IoT type ideas, but and of course, an example of IoT is a grid, a smart grid, right? So I mean, it does apply there. There are I don't know about energy companies, but Department of Energy is interested. So
Okay.
they're definitely interested in the privacy issues that I just discussed, having to do with data collection at the edge of the electricity grid being used for, say, machine learning to try to optimize the grid. I'm working now with some other people on a Department of Energy study where that's one of the big issues is privacy preservation at the edge.
Okay.
So
Cool.
I don't know whether, and of course, the idea, of course, DOE is interested because eventually they would like for the utilities to be interested in that. And we have partners who are, national labs that work, on these problems. So, I mean, the idea, of course, is ultimately to transfer to practice. So, yeah, I think there is an interest in that. I mean, as the whole point is that, the traditional electric grid is very centralized. So there is no data from the edge, and it's all there's no decision making at the edge. But with the renewables and storage and so forth, it's much less centralized now, and there's a lot of more decision making at the edge.
Right.
And that's two-way communication, which is part of that, is privacy revealing. I mean, it reveals information about the end user. So all of a sudden, or maybe not all of a sudden, but now there's a lot more interest in these kind of issues. They weren't as worried about it when all the control and all the information flow was downstream. But now that it's upstream and there's consumers involved, it's much more important.
Okay. Vince, there's a question here from one of my colleagues, Jonathan Scarlett. He's an information theorist who works at the intersection of information theory and machine learning, and he has a question.
I know his work.
Okay, yeah. All right, great. So
I don't know if we've ever met, but I know his work.
Okay. All right, great. So John asks, in a way, practice has caught up to Shannon's communication theory. To what extent is that true for these problems, and how do you think that will go in the future?
That's a great question, John. So I think I don't think practice is anywhere near caught up with the theory here. I think this is more like Shannon's information theory back in the 50s when people were developing codes and everything, but they weren't anywhere near capacity or anything like that. I think that's where we are with this. I don't think it's a long way to go before we can feel comfortable that we've milked this for as much as we can. So I think we got a ways to go. Yeah.
Okay. Thank you, John. Thank you, Vince. So anyone else have any questions? I can also arrow my team. Hamao or Taekwe or Teng, any questions from the viewpoint of coding?
Well, it's okay. It's late over here, man.
Yeah. Okay, great. Okay. So I think great, thanks. So thank you everyone, and thank you Vince for the awesome talk. And please keep in mind, Vince, we're going to keep you in the loop. We'll send you the reminders about the other talks. We have 4 more talks lined up for the rest of 2020. And we're gonna restart this again in 2021. So Vince, we'll keep you in the loop, and hopefully you can join us. Probably the 5 p.m. talks, which would be 4 a.m. for you, are probably a bit hard, but at least the 9 a.m. talks, because what we are doing to let everybody know, since the speakers are worldwide, we picked 2 times, 9 a.m. Singapore time and 5 p.m. Singapore time, right? Depending on, let's say, to make it as convenient as possible for the speaker and also for people in Singapore and Southeast Asia. Okay, so please be on the lookout for emails for us. And next Wednesday, Hanma, who's on next Tuesday at 9 a.m. is, do you want to just say who that is?
All right, so the next speaker is Venkat Guruswamy from CMU. Carnegie Mellon University. Since Prof will talk about catching up to Shannon's communication theory, he will be talking about polar codes, where the title is Arikan meets Shannon.
Yeah.
So about how polar codes is trying to catch up with Shannon's information theory. Information capacity.
Yeah,
So
he's a theoretical coding theory person. So
yes.
Computer scientist. A computer scientist essentially. Yeah. So please come for that. And remember, every Tuesday until the end of the year, we have a talk, and then we'll probably start sometime in mid-February after Chinese New Year. So that's the plan. Okay. So everyone, let's, if we don't mind, let's give Vince a virtual round of applause. I think if you go into Zoom, you can actually do a hand clap. So if you go under more, in the participant window under more, you can see hand clap. So I've done my hand clap, and once again, thank you very much, Vince.
Yeah, thank you, Mayo. Great to see you, and thank you for inviting me.